Yeah, so today I'm going to talk about hacking Shannon Baseband. I'm Natalie Silvanovich, and I'm a team lead on Project Zero at Google. And recently, we started talking about baseband. No one on our team really knew much about baseband. We, of course, knew that there were exploits and there were bugs found pretty regularly, but we weren't clear on, especially, how long would it take to find such a bug? And also, let's say you had a great bug exploited. What could you do with it? So we had the idea to do a Baseband Hackathon. We got about 5 people together to work on this full-time for 2 months, and we wanted to see what we could accomplish. So we decided to target one of Google's own devices, the Pixel 7. And it turns out that the Pixel 7 has a Samsung Shannon Baseband. It's a special chip for this device, the G5300, but there's a Samsung S5300 that's pretty similar. And, of course, when you want to look at baseband, the first thing you think is, I need a software-defined radio. And we did find one we could borrow, worst case. But we found out pretty quickly that we didn't really have the skills to do anything useful with it. And also we discovered there's a bit of a difference between someone saying, sure, borrow my equipment anytime, and actually letting you borrow their equipment. We also thought about what our attack surface should be like. And there are baseband attacks that involve compromising the mobile infrastructure. But we decided not to pursue that either. We specifically looked at the scenario of what if you have an attacker who is on a mobile device who wants to, like in this bad clip art, reach into the victim phone and get data off of it. What's possible with regards to baseband hacking? So a lot of presentations I do are on work I did myself, but this one is not. As I said, there were about 5 full-time people working on this hackathon, so I want to thank everyone who was involved here. It really took all of us to push this little baby of our first exploit, baseband exploit, and get it walking. So to start off, what does a cellular network look like? This is a very, very simplified diagram. But TLDR, you have a person who makes a call, and their phone talks to a cellular tower. And then in this day and age, either it will go over cellular towers all the way to the phone where it gets the incoming call, or it will go over the internet in VoLTE, and that person will get an incoming call. And typical baseband exploitation, at least what we'd heard of, has an attacker who is here. They have proximity to the victim's phone, and they attack it by pretending to be a baseband, usually using a software-defined radio or something similar, and they try to find bugs in the protocols that get processed that way. And we thought about what the attack surface there would be. And one possibility is 2G. 2G is an early mobile protocol. We are now at 5G. And unfortunately, we discovered that only with 2G can you access a lot on a target phone without authentication. Once you go to 3G and higher, not as much attack surface is available. But one attack surface that was available was ASN1. And we looked at this a bit, and we thought maybe it was old news. We didn't find any bugs, and we thought, maybe all the bugs are gone. Now, funnily enough, I went to OffensiveCon last week, and there was a guy there, a Matt Kama, who was doing a talk on how he found all the ASN1 bugs. So it turns out that maybe he found the very last bug, and they were all gone after that, and there's no more bugs in this. Of course, that is not true, but I think this is an attack surface that has less low-hanging fruit than maybe other stuff we looked at. And the other problem is if we wanted to get serious about it, we would have to figure out how to use an SDR. So there's also the potential that you compromise a network. As I said earlier, this is not something we pursue, but it is an area where a lot of other attacks have been considered. But then we thought about this attack scenario. What if, instead of being in proximity of the phone or having compromised a base station, what if your attacker is the person who's calling you? And I thought this had a lot of potential, specifically because I spent a lot of time looking at WebRTC. And WebRTC is basically the library that powers all video conferencing on the web. It's used on browsers, it's using mobile phones on things like Signal and Facebook when you do video calls. Even platforms that don't use the actual WebRTC library, like WhatsApp and FaceTime, they use protocols that are very WebRTC-like. This diagram is basically how all video conferencing works. And the idea is that you have two nodes that can talk to each other, two Facebook clients that can send a message to each other, or, two phones or two browsers that can communicate over WebSockets. Then you exchange a piece of information in Session Description Protocol, SDP, and that is your crypto keys, that has your protocols that are supported, and routing information. Then you start a peer-to-peer connection, and that's how you get your audio and video transmitted from one device to another. And it turns out that VoLTE is not that different from this. It once again has two peers that can talk over these base stations, and then they exchange information, and then they get P2P protocols. And I thought this had a lot of potential, because there was this attack in 2019. And if you've seen any of my other talks, you've probably seen this slide before. I have been using it in almost every talk for the past 4 years. But it's because it really changed the way that I thought about fully remote attacks. So what happened here is some attackers managed to compromise people who use WhatsApp. And the way it worked was they called the people several times, and protocols were exposed, and they found bugs in those protocols, and that ended up being a fully remote attack surface. And this was something, with regards to WebRTC, I thought was a possibility. And in 2020, I spent a lot of time writing a WebRTC exploit and making it work on Android. And I basically found that you could use WebRTC to compromise a lot of Android applications fully remotely. And if this works, why wouldn't this work on VoLTE when VoLTE is so similar? So I investigated further. So what does the attack surface look like for a baseband modem over VoLTE? Well, there are a few protocols that get used. To start off, VoLTE sessions are initiated with Session Initiation Protocol, SIP. And this is a server-mediated protocol, so both sides have their own server that they talk to, and then the servers communicate. And this contains the information that is used to set up the call. Then, within SIP, there is the Session Description Protocol, which I mentioned is also used in WebRTC. And this contains all the connection information for the two devices, basically how they can talk to each other over the internet. Then, once they establish this connection, they talk in real-time transport protocol, which is typically peer-to-peer, which encapsulates a codec. And the codec typically used for VoLTE is H.264. And I have an asterisk here, your user space may vary. Because depending on what baseband you use, depending on what device you use, these may or may not be in user space. On the device that we looked at, the Google Pixel, SIP, SDP, and most of RTP are actually on the baseband modem. Meanwhile, things move to user space to do the H.264 decoding. This isn't true on every device. I also took a peek at an older Samsung Galaxy, and this one has SIP, SDP, and RTP all in user space. So it really depends on the device. So after this, I wanted to investigate more. So we started off by dumping the baseband. This has been documented a lot, and it hasn't changed. So if you're looking for a source of this information, I would suggest looking at the slides of this presentation, A Walk with Shannon by Amat Kama. And once I had my dump, I loaded it into IDA. And these dumps are really convenient for that. They basically just start at a specific address, and then it's the full address space. And so then I located the SIP and the SDP processor, and this can be done based on strings because these are both text protocols. And I did look for RTP, and it was more challenging. Honestly, I'm still researching this. I didn't get a great opportunity to look at it. At first, the execution flow was unclear, and I didn't find great strategies for this. Honestly, the best strategy I could come up with was to guess, hope I found a bug, exploit that bug, and then once I exploited the bug, I could start putting undefined instructions in different locations, and then I could be sure that code was part of the execution flow. Yeah, but this was, not an ideal situation, and one big walk away from this talk is I think we need way better debugging for baseband if we're expecting people to do mature vulnerability research. So, once you crash, you get a crash dump. You can also initiate a crash dump as well. The secret crash dump screen is you type in this code on your pixel, and then it jumps up, and it'll give you the option to crash right now. It'll let you copy your crash dump from one part of the phone to another. It'll also let you turn on and off the test heap, which is often useful, because often when you're using a rooted device, that'll turn on the test heap, but if you want it to simulate a real heap, you need to turn that back off. The other thing, someone's already contacted me on Twitter about this, so I also want to say that you do need to turn SE Linux off and have your device rooted for this to work on a modern Pixel. So once you get your crash dump, you load it at address 400000, and it also has a lot of other cool stuff that I'll talk about later. And then once you have the crash dump, if you call strings on it, a little bit of the log before it crashed is in there, so you can use that to dump the registers, because it'll say where the registers were at. Unfortunately, there was no logging on this device. We didn't have any logging when we started, and we never did get the capability to read the logs off the Pixel. There are some leaked Samsung tools you can find online. There's also an open source tool called SCAT, but unfortunately the Pixel is different enough from the Samsung devices that these didn't work. So code exec really helped with exploitation. So then we started doing code review, and now there is a part 2 to the question of what code can be reached. There is it on a code level, so basically, when you look at this dump, there is so much code, and I swear like half of it is never used for anything, or it's test code that doesn't get linked in, that sort of thing. And that was basically all you could do is analyze and then do the thing with the undefined instructions. But then there's another practical concern here, which is if we're talking about SIP, if we're talking about SDP, and I'm doing it from a phone, that's not going through my network, it's going through somebody else's network. And can this malformed SIP or SDP actually make it through? And this is typically where filtering happens. And I'm going to talk about filtering, but that's not really what happens here. What happens is you're using SIP, which is the server-mediated protocol, to set up the call. And this, because it's server-mediated, it needs to be processed. This isn't filtering. The SIP server needs to parse this and analyze it before it can send the request to the next server. So this means that kind of for a successful bug, you need your whatever you're sending your proof of concept to be able to be parsed and re-encoded successfully. At least this is true for some protocols. So SIP and SDP, definitely every server we looked at on carrier infrastructure would need to successfully parse both SIP and SDP. Meanwhile, things like RTP and H.264, those are kind of peer-to-peer protocols, or they are mediated by servers that don't do as much in-depth analysis. So these are ones that, maybe you could do a real wild proof of concept and the carrier infrastructure wouldn't notice. But unfortunately, they weren't zero-click. It turned out that there was no overlap between these P2P protocols and the zero-click attack surface. Either you could find a bug in SIP or SDP, and then that is a zero-click bug, but you have to get it through carrier infrastructure or you're going to have a problem. Or you can find a bug in RTP or H.264, but those require the user to pick up the call for the exploit to work, and that's just not as good an attack. So we ended up looking at SDP and SIP. And just to make it even clearer what I'm saying about the server processing, I'm going to give an example of some SDP. And this is what SDP looks like over the network. It is a text protocol. And what a server will do, usually they're in Java, but sometimes they're in C, is they'll process this. And this first bit of the M line, let's say that's what's being parsed, has to be either audio or video. So most servers, when they're parsing, they won't store that string. They'll turn it to an enum and then put it in a struct. Meanwhile, the port is an integer, so that will usually be stored as an int. Meanwhile, there's this string protocol, which represents the protocol that the audio is in. And this one's kind of a toss-up. Some implementations I've seen of SDP processing, it will store it as a string. Though there also are a limited number of protocols, so some of them just use like a really large enum and use a number instead. But let's pretend in this case this particular parser makes this into a string. This is kind of telling about what sort of bugs, might make it through the server versus which ones might not. So like, let's say I replaced audio with AAAA. That is probably not going to make it through the server, because that's going to be converted to an enum, and then, you might get an error, you might get 0 back, but you're not going to get AAA back once it decodes. Meanwhile, if you put a string in something like the protocol, depending on the implementation, you might get that back. If the decoder stores it as a string, and then when it re-encodes, it gives, it just doesn't check that string, you might get that back. And that's basically what we found, that there were some things like, changing the audio to be a string or making the port not a number where you would never get that back, but a lot of strings would just go through encoding unchecked. So, some observations we made. Malformed stuff would often get through, but sometimes not. We found that servers were less sensitive to malformed SDP versus SIP, which makes sense, because SIP has to be reasonably correct and parse for every call for the next request to go. Meanwhile, for SDP, the intermediary server doesn't look at it so much. So long as it's reasonably valid, it would usually get through. Another useful thing about SDP is that once you've set up the phone call once, the phone actually remembers the connection information for a bit. So if you have really malformed SDP, you can do one call that works correctly. It doesn't have to be answered, just it has to be established. And then the next time, if you have really malformed SDP, that doesn't cause functional problems because it will use the information from the previous SDP. So that made this very useful for bugs as well. We found that this filtering varies greatly across carriers. Some of them would let basically anything through, and some of them were really sensitive. And also another thing to note is these text protocols have reserved characters. Like, if you look at this, a space means something, a new line means something, an equal sign means something. So this, once we got to the exploitation stage, this is a limit. So, one thing we wanted to do was separate the question of, is a bug real and reachable from, is a bug being blocked by the carrier? So, a couple of years ago, a few people on the team went to baseband training with Marius Munch and Dominic Meyer, and they gave us this unicorn emulator for baseband. So we made it run with the image from our Shannon Baseband for the Pixel, and this allowed us to test individual functions. It isn't a full booting emulator. We couldn't, pretend to be a base station and send stuff, but we were able to call a function like the SDP function and test stuff. And this allowed us to, figure out things like, is there really an overflow in this function, and that sort of thing, before we started messing with carrier stuff and seeing if we could get it through. So, yeah, we reviewed the SDP and the SIP parsers based on the strings and found a lot of bugs. And then we fussed it with this emulator, the functions we thought were the most sensitive, and found a lot of bugs that way as well. So here are some of the bug highlights. This is a bug in the accept type format in SDP. And it's actually kind of a simple bug. So in SDP, this accept types line gives you different formats that are supported, and it's stored as a standard string by the modem, but it assumes you have less than 12 types, and it copies into the array, and if you have more than 12 types, it will just overflow this array with basically a stud string pointer. Then there is a similar bug. This is in the chat room attributes, which is the name of the different chat rooms for things like RCS, and it had basically the same problem, that it assumed you would have no more than 12 chat rooms, and if you have more, well, too bad, you've just corrupted memory. Then there was also this bug, and this was in the configuration types in SDP. And this was another size issue, so the configuration types are integers, and it would assume, I don't know where they get these numbers, that there would be no more than 14 configurations, and then it would translate these to bytes and store them in this array. And this was actually kind of a nice bug, because the previous one, you're overflowing, but you have to overflow with a string. Meanwhile, this one, it would call ASCII to int on these and overflow with bytes. So this meant you had an overflow where you could basically control every byte and make it any value with no restrictions. And finally, there's this bug. And this bug has an asterisk in that this is the type of bug that doesn't always get through carrier infrastructure. This bug is that this format protocol line has a number as its first parameter, and in the intermediary processing, it assumed this was an integer without checking, so it would copy it into a string of length 8. And a lot of SDP parsers in the intermediate carrier infrastructure would get rid of this, so it wasn't a great bug, but it was kind of an interesting one. And just so you know, these were all fixed on March 6th of 2023. And finally, I want to give an example of a representative SIP bug. This one was reported by Yvonne Fratrick on my team, and he found about 6 similar bugs using fuzzing, and they were all kind of like this, where SIP got processed and would make assumptions about a string buffer size, and then use string copy to copy them, and lead to an overflow. And like the previous bug I showed, this was hard to get across carrier networks, because SIP actually influences how they behave, so if everything's not perfect, they don't work very well. But it was interesting that this component was so buggy, and this bug was fixed on April 10th of this year. So, next step. Got to try these bugs on a real network. So, I used a rooted Samsung Galaxy S9. This was one of the phones that did this in user space, so I could hook this using Frida and then change the SIP and SDP. The Galaxy S9 uses resip, which is an open source library for SIP and SDP, and I'd actually looked at it before, so it was pretty easy to find where it processed this stuff. And then it was possible to alter the SDP or the SIP that got sent. I found that the filtering behavior is different for different carriers, but I don't think there was any carrier that filtered perfectly. All of them let some of these bugs through. And it was the caller carrier that mattered the most, because you can have a caller and a callee with different carriers, and I tried, what if the caller and the callee are different and that sort of thing, and it was really the caller's carrier which mattered the most here, which was actually good, because at least if you're an attacker, because it's the attacker that decides what carrier they use. Yeah, and these 3 SDP bugs I showed first, they worked in a fully remote context on most devices. So, now it was time to exploit the bugs. So I just want to review what the capabilities of these 3 bugs we could get through consistently were. There were 2 that were fixed size heap buffer overflow with strings. And this was the one where it was an array of 12 strings that you could overflow with more strings. And this ended up being, I think, 120 bytes, because strings are more than 8 bytes long. And the overflow size was controllable. You could overflow it with as many strings as you want, but the size of this initial buffer flow was not controllable, and what you overflowed it with was only sort of controllable. Then there was this configuration bug, and this one had a different, a 14-byte buffer, and you couldn't change the size of that, but you could overflow it as much as you want with any values you want with no limits. So another thing to think about for exploitation is what are the security features on this modem, and I would say honestly not great. There's no ASLR. There were stack cookies that actually changed on a regular basis, so that was good, but I didn't have any stack bugs anyhow, so didn't really help here. And there was limited heap corruption detection. I would say it was actually kind of unfortunate in that they had heap cookies, that the heap cookie was always the same value, which was AAAAA, and then if you overflowed it and corrupted it, what the device would do is it would notice and then return without freeing anything. And, sometimes this made things worse, but most of the time this made things easier for exploitation, because this meant that you could try as many times as you want, and if you didn't get it right, it would just be like, nope, and return gracefully. So that made things easier. Finally, there was a non-executable stack and heap, and a lot of exploits that I saw in previous presentations kind of dealt with this by finding, secret areas of memory where this was not true, where there were read, write, execute pages, that sort of thing. On this modem, there were 0 of these. Everything was either read, write, or read, execute. So that was something we had to get around. So then we looked at this heap a bit, and this is a heap chunk on the Shannon heap. And there's kind of 2 interesting features here. There's the heap ID, which represents what algorithm is used to free and allocate, and then there is this cookie. And this is the not very good heap cookie I told you about previously. And then what else is here? Slabbiness. This is a slab allocator, which I consider to be a problem in this particular context, because I've done a fair bit of fully remote exploitation, and the way you typically have to exploit a slab allocator is that because there's no inline heap header, you have to find an object that is the same size, and then you have to overwrite that object, and then hopefully find one with the right pointer that allows your exploit to work. And if you're doing this in a browser, it's a pretty good way to do this. But when you're doing things fully remotely, you don't have a lot of control, it is really hard to manipulate the heap, it is, hard to guarantee that, someone else isn't sending you a packet and messing everything else, etc. And I have spent, weeks and months trying to get this to work, and it never does. And so, in my opinion, the best way to get a fully remote exploit to work is to make the thing that makes your exploit work in terms of execution as close in proximity to the bug happening, because that reduces the risk that anything unexpected will happen and make your bug not work. So, I looked a bit further and started to wonder, wait, what is this heap ID? And it's an indicator of the heap type. But what was surprising was that the heap actually relied on this. So if you overwrote this value, it would change the algorithm that got used to free this chunk. So we looked through the heap algorithms, and we found heap 6. And heap 6 is kind of similar to how allocators work on Linux. It's a linked allocator. And it, of course, had unsafe unlinking. So we were able to overwrite this heap 4 chunk and create a fake heap 6 chunk, and then get freed with that allocator. So here's some of the code from this allocator, and it actually kind of has a nice feature here. You'll notice at the bottom there are no safe unlinking checks, which is nice. It means that if we do a fake header, we can get an arbitrary overwrite. But what's also interesting is the location of this header is also determined based on something from the heap, which makes this even better for exploitation, because then what will happen is it will free this heap chunk, and then it will grab this, and then that'll let you tell it where the rest of the heap chunk is. So this means, if you have any values you gotta skip over, if there's any area you can't change for some reason, you can just move this to happen somewhere else, and it makes your exploit work. So the first attempt is, I tried to use this configuration bug, the one that overwrote 14 bytes with any number of bytes with any value. This one was disappointingly difficult to exploit. The problem was that there's not actually that many chunk sizes on the Shannon Baseband. I think the smallest is 32, which this 14-byte one would get into that class. And there was so much heap contention. There were things being allocated there nonstop. And it actually turned out to be weirdly hard to overwrite an active buffer. It was much more likely that the buffer next to me had already been freed by the time I overwrote it. So I did kind of get an exploit to work like this, but it would sometimes take even 5 minutes for the exploit to work, because it would just be churning and churning and churning, trying to find an active one, and trying to overwrite it at the right moment. So this was not great. It also had another problem, which is, where do you put your shellcode? So you've got one 4-byte overwrite. What do you do next? So I would say I would put this attempt into the sorta worked pile. So then we started looking at this other bug. And this one overwrote 120 bytes with a standard string. And because of this buffer rounding and the limited slab sizes, this was a 256-byte buffer, which turned out to be kind of a rarer type that didn't have as much allocation contention. But what's also nice about this bug was that you could get other allocations of this size to happen during processing. Because the way this works is you have the different format types in an array, and then you overflow the array. So if you make the format types also 120 bytes long, you can get, format type, or it'll allocate the array first, but it'll do array, format type, then it will start overflowing them with the pointers, and that means you can overflow something that you actually control. So that made it possible to do some other things. Now, one of the problems here, of course, is that you can only overflow this with strings, because this bug doesn't allow you to control those values. But that was where this feature of the heap was really nice, because you could make it so that you lined up the length of the string with this value that got added to the header, and then you could make it be in the middle of the next string. And then that would allow you to control all these values for the arbitrary overwrite. And just to make this a little bit clearer, this is what this actually looked like. So we would have the long array, and then the first two are 128 bytes long, so they get allocated. And then this would make the crash occur, where in the middle of this string, it would try and do the overwrite. So what next? We ended up overwriting the free function pointer. I mentioned earlier that there's a debug heap, and then there's a real heap. And the way this works is, at a very high level, there's a pointer that points to the free function for the heap that you're actually using. So we overwrote this, and we had to do it unaligned, because one of the problems about these arbitrary overwrites is they go two ways, right? You think about them like, oh, I can overwrite anything with anything. But really, you can overwrite anything that's mapped with anything that's mapped, or else you're going to get a crash right away. So we dealt with this problem by writing only the bottom 3 bytes of this pointer, and then we could make the most significant byte something that was actually mapped, so that when it did the second write, it would just write somewhere arbitrary on the heap, and we'd still be able to overwrite this pointer. And then we were able to use a few heap gadgets to get to the scatterload RT2. So, scatterload RT2. If you've fallen asleep during this presentation, I would suggest you open your ears right now, because I think this is the most interesting thing you're going to learn. So, we found this gadget that is just super useful for exploitation. It's part of the ARM OS, so I think that almost every ARM device is going to have this in there. And what it does is it goes through a heap vector, and it pulls out the first value, and that's the function it calls. Then the next three values are the parameter, and then it loops. It makes the call, then it loops, then it does another call, then it does another call. So this is super useful because this means you can call as many functions as you want with as many with the parameters you can control. And this allows you to kind of set things up to get your exploit really working. Because the next problem is that I couldn't execute code from the heap. I actually couldn't execute code I controlled from anywhere. Even if I overwrote it, there was nowhere that was both writable and executable. So I ended up finding this gadget. So non-executable memory is controlled by the domain access control register. They create different domains with different privileges. But you can just set them all to permissive. So that's what I did. I used this gadget to set this to FFFFFF, which meant then that there was no access control on memory. And at this point, it made debugging very difficult because, if you're accessing an invalid address, you're just going and going and going. But it did allow execution out of the heap. So now time for shellcode. So we could now execute them from the heap, and there were a lot of forbidden characters, but no length limit. So this was pretty reasonable. I ended up just writing shellcode, as I wrote it, checking that the characters are not wrong, and then changing it. If you really have a problem, I think there's a Metasploit module that can do this. There is one problem, which is that this stacker thing only works in the thread that you're in. If other threads try to execute stuff out of the heap, they still can't. And the way we got around this was that there was nothing stopping us from overwriting executable pages at this point. So if we needed another thread to execute code, we'd overwrite some code that wasn't really being used and with code we wanted, and then it would be able to execute code from there. So now what? So this is possibly the worst demo ever. Our proof of concept is, you'll notice Yvonne, he is sending a text, and then the text that arrives is a different text that says hack. And that's because we compromised the phone so that it swaps out the text messages. And I think that was the best proof of concept we could come up with in a short period of time. So now the real now what question. What can we actually do with this that is useful? So one thing you can do is you can see what people are doing on their baseband. And this is, not trivial. It has all your phone calls going through it, all your text messages, sometimes your internet. So I've seen, proof of concepts where people do stuff like make internet access go through a proxy or intercept calls. And, depending on the type of attacker, this might be what you want to do. But recently, my current research is to try and find ways to escalate to the application processor through this. Currently, I've been looking at the driver that communicates with this baseband processor. So the way it communicates for things like packets is it will use shared memory that both sides write to via PCI, and then there are interrupts, and there's also MSI interrupts, which are a PCI feature that are used to make this work. And this is a fairly large attack surface, so I am optimistic that I might one day find a bug in it, though that hasn't happened yet. The other thing I want to mention is, how I said there was lots of cool stuff in the Crashdumps? One of the cool things that's in there is all these memory pages. It will copy them and output them before it crashes. So if you want to investigate that sort of thing, there's lots of cool stuff in the Crashdumps that will help you. So what did we learn? So we learned that if you have 5 people work on a modem for 2 months, you can't compromise the modem, at least for the Shannon Baseband modem. So that gave us a feeling for how long it takes to get a good result. All considered, we found this to be a pretty bug-rich environment. I spend most of my days trying to find bugs in mobile software, and I would say this one was a step below. that it was easier to find bugs, and the type of bugs we found were more useful. So I think there can be improvement done in that part of modems. Lack of tooling was a major barrier. It was probably the biggest barrier we had to deal with. The real problem with these baseband modems is it's almost impossible to figure out what's going on, and it's more difficult without code execution. I think, unfortunately, that baseband modems are kind of like iPhones with regards to hacking. You know, you have to stay one bug behind so that you have a jailbreak that you can use to do development. And that's unfortunate, because I think that, you know, that's a big barrier for someone getting into this to even have one bug. And it means that, you know, even well-meaning researchers aren't going to report everything they have, or else they're going to get cut off. Fully remote baseband attacks are a possibility. Walking in, I did not think it would be possible to compromise baseband from another phone, but here we are. Another thing that was unexpected about this is, you know, there's no proximity requirement. I've tried this, you know, across continents, and it still works. Finally, Shannon mitigations have improved compared to the research I looked at, but they're still lacking. You know, if I had to pick, you know, two things, ASLR would have made a big difference here. I think this would have moved this from 2 months to 6 months or even more, because we would have needed to now find bugs that would give us information about where things were on the heap and where things were in memory generally, and that would have made things more challenging. Also, heap hardening, I think that would be a big win. The fact that we got infinite tries on the heap, the fact that we didn't have to guess anything, that it was always AAAA, made things way easier, so I think that's a big area for improvement. So that's it. Thanks a lot, and I think we have a few minutes for questions.